Okay, so my name is Antti Tarvainen. I work for Curious AI, and I'm going to present you 2 or 3 papers about residual networks. So residual networks are a technique that was first published about a year ago, I think, and they are state-of-the-art in fully supervised image recognition at the moment. How many of you know how deep learning works, deep neural networks? Okay, and what about convolutional neural networks? Okay, and residual networks? Okay, yeah. So, well, you'll see. So, okay, so deep learning. There seems to be a progress where the deeper we may make our networks, the better what they work, if we can make them work. So the problem when we add, oh, by the way, I should tell you, these are not my slides. I'm just copied the presentation from Kilian Weinberger, and so he's a professor at Cornell University, and the work is by his students. I think Gao Huang is the main author of this paper. Okay, so and this is stochastic depth is the name of this paper, the first paper I present. So okay, the problem with when we increase depth in the networks is that although we get good training error, the testing error suffers. So they don't generalize as well. And one way to think about why that happens is that if we think of the network as a game of telephone, so here we see that the input is a car, and then the different layers tell each other like what's there in the picture. That like when everything goes well in the training, then all the layers say that it's a car, and then the output is a car. But then when in the test set we see a different car, then when one layer makes a mistake, then all the layers after that make a mistake as well. So so it's enough for one of the layers to go wrong, or if one of the layers goes wrong, then all of the layers after that they won't help because they get a bad input, and then they'll have a bad output as well. So this is more likely to happen when there are more layers, and unfortunately it's undetectable during training, so we need to figure out a way to do that, to work around that. Oh, I just put the time I have for 17 hours, which may be too much. Oh, okay, never mind. So, okay, we want to reduce the impact of the bad layers, and the stochastic depth is a way to do that. So stochastic depth works on top of residual networks, and residual networks are the idea with the residual networks is that between all of the layers in a deep network, we add this identity connection, which means that after each layer we sum up the result of this layer plus whatever that was the input to that layer, and this is good because it helps the when we train the model, the gradients, so the updates that each layer should have, it lets the gradient flow more easily to the first layers, and so it's easier to train these kind of networks. So it's a good trick to know, and it's improved the results on image classification by something like 50% a year ago. So the problem with the residual networks is that the layers can still work too perfectly during training, and they there can be a reliance on any of the layers, and then the rest of the layers don't work well if one of the layers doesn't work well. So the idea of stochastic depth then is that for each of the layers we flip a coin, and then if that's a head we keep that layer, and if it's tail then we remove that layer, and we can then we just train the network using just the layers that are left. what does this animation do? Okay, so that's an animation of training. Okay, one minor detail. Okay, well, okay. Here's first a presentation how that works. So for different images, we drop out different layers, and one minor detail is that we don't drop the layers with equal probability, but the first layer is not dropped out at all, because if we didn't have the input image at all, then we couldn't do anything or couldn't predict anything from that. So we always skip that, and then the last layer we drop with 50% probability, and in between linearly. So different layers or different images, we drop different layers, and so with all of the examples, we use different layers, and this means that we don't rely on any of the individual layers. And then during test data, we use all the layers, but we weigh them so that with the probability that we use to drop them out during the training, so that the average output of each layer remains the same during testing and training. So what we actually do is that this is an ensemble of so this is an implicit ensemble of many models, and so it learns to work regardless of which layers we have left. It's also quicker to train because it's shorter during the training, and it has an improved information flow. So it's even easier to get the gradients to the first layers. Okay, and if we look at the results, well, first of all, this is built on top of ResNets. It uses batch normalization, and dropout is a similar idea, and not going to go into more detail on that. So built on top of these, and if you look at how it works compared to the original ResNet, well, it's better, but what we can do with the stochastic depth is that we can improve or make the network even deeper. So now we can do deep networks that are even 1,000 layers deep, and that's this deep, if you must know. So that improves the results even more. So with this idea, you can train faster, train deeper networks, and obtain a lower test error. Okay, so that was the stochastic depth. That's a paper, stochastic depth. It's a really interesting idea. I'll return to that. Why I think it's especially interesting in a few slides. But before that, I'll present another idea from this group, which is related. So do we really need to have so many layers? So 1,000 layers, can we do with less using the same ideas? So I don't really remember what this slide is about. Well, I think the idea is that with stochastic depth, we don't rely on any of the layers, because none of the layers is too important, but it also causes an enormous amount of redundancy across the layers. So each of these layers, the parameters that each of these layers has to encode pretty much the same information or related information. So there's a lot of redundancy across all these layers. So what we can do instead, before that, how we can think about this is that because of these skip connections in the residual network, there's actually an implicit connection from any of the layers to any of the following layers. If we think of it like this, then we can ask, why do we need to play this game of telephone at all? Why can't the layers just talk directly to each other without any of the intervening layers? And that's the idea of this second paper called dense connectivity, where we, instead of having a ResNet, we modify the idea and actually add a connection from every layer to every other layer. Okay, actually, because we might want to also change the size of the layers in between, we actually do it so that we divide the entire network to blocks where the dimensions don't change, and when we change the dimensions, then we within each of these blocks we only connect to between all of the layers, and between different blocks we only have one connection. So this also removes the reliance on any single layer, because all of the layers get input from not only the previous layer but all the previous ones, and this also solves the information flow through the direct connections, and this doesn't introduce redundancy between the weights. So now the different layers don't need to encode the same thing because we are not dropping them. But you might ask, like, how? But isn't this an enormous number of weights? Now, like previously, one layer only took the input of the previous layer. Now we have to consider like it taking possibly from 10 different layers the input. Doesn't that mean that the number of parameters that we have in our network has grown by the factor of 10? Well, no, because we can now, because of this, we can also make each of the layer much smaller. They don't have to add so many new channels, or they don't have to. Or it's enough for each of them to just add a few channels, or to the previous input. So in fact, this can reduce the number of parameters, and we can so we have reduced the number of parameters and we have improved the results. But then, well, if we now have a lower number of parameters, what if we add more parameters? so then this becomes even better. So this might be the state of the art in Cypher 100 at the moment. So Cypher is an image set where there are like small pixels of animals and other stuff, and you have to recognize which class each image belongs to. I think Cypher 10 has 10 different classes, and Cypher 100 has 100 different classes. But these are only small data sets. So the actual image recognition is of course done with like much larger images. The ImageNet dataset is for that, or it's closer to realistic size images, and that is the kind of like I think that is the like what is really used for comparison between like what is currently the best technique, and this DenseNet also does very well there. Because this is work done by a university, by a group in a university, it means that they don't have the computational capability that Google, for instance, has, and so they haven't done like the full training with this, and they don't know how good this actually could be if they did have a longer training. Okay, so to sum up these two papers, like if you do image classification with fully supervised data, use ResNets with stochastic depth, or even better, use dense connectivity. And the code is available, and these are the people who had done this. So why I wanted to talk about these two? Well, of course, like image classification is important, and it's good to know the latest tricks how to make that work. But I think it's also adds up to our understanding how neural networks actually work. So why is depth a useful thing to have in neural networks? And there are two ways to think of that, and so kind of like when you go deeper and deeper in a network, you can think that the level of abstraction grows. So like the very first layers are about recognizing lines or corners, and then later layers may be about recognizing eyes, and then like the last layer is about recognizing whole people, entire classes of animals, or stuff that people do, or something like that. So when we go deeper, we get more higher level of abstraction. But then there's another way of thinking of this, and that's like thinking of it as a progressive enhancement. So the very first layers are just like crude approximations of some features, and the later layers are like better approximations of the same features, so that the features don't change, but they like we are just getting better and better approximations of what those features are. And before, I'd say last year, most people would have said that this level of abstraction is the way to think about it, and this is what mainly happens inside the networks. But then what ResNet showed us is that because of these skip connections, because like each unit in a layer is connected to the same unit in the previous layer, they must have, and we just sum them up, they must somehow encode the same features. So because ResNet works, it must be that the progressive enhancement is a big part of it. So there might be, I think there is when we go deeper, we get more and more abstract features, but this progressive enhancement is also an important part of that. And what these, especially the first paper that I talked about, the stochastic depth, shows that if we if we think about it this way, it helps us design better algorithms, and then it helps us think about it, and it helps us design better algorithms and get better results. I mentioned quickly a third paper here. So this wasn't a NIPS, but this was mentioned there in a presentation. I think this was from this month or last month. So this is from Google, and it uses a similar idea as the stochastic depth. So also here we don't use all the layers of a residual network, but instead of like dropping randomly layers out, we learn at which point we can stop the computation, and it depends on the input image that how far we go inside this network, so that we look at the features after each layer, and then we decide, do we need to take another step in the calculation? And they show good results. And what's interesting here also is that we can do this pixel-wise, so that we don't, for each of the pixels of the image or each location in the image, we can choose different points to stop. And if we do that, then we get interesting images about where the network should spend its time in computation, or where it spends its time on computation. And I think this is another idea. If we stop thinking about the abstraction that the different layers bring, and start progressive enhancement, then we can design better algorithms by taking that view. And some more images from that paper. Okay, and that's all I have. Any questions?